Lesson 9.6, Area and Arc Length in Polar Coordinates. Let's continue our investigation of polar curves related to areas and arc lengths. When finding areas in rectangular coordinates, we used rectangles to approximate the region. That was our LRAM, MRAM, RRAM. We were using those rectangles. In polar coordinates, we are going to use sectors of circles. So another small change will be in our language. In rectangular equations, we found the area under the curve. With polar equations, we will find the area enclosed by the region of the polar curve. So what we're going to do is we're going to take the circle and remind ourselves what the area of a sector is. So if this was a sector of the circle and we wanted to find this area, we know that our radius would be on both sides r. We know that we could look at our angle theta as our central angle. And we would be thinking of this piece as a fraction of the area of the whole circle. Okay, it is a fraction of the area of a whole circle. And so our sector area would be equivalent to a fraction theta over 2 pi of, which means multiply, the area of the whole circle. And you can see here that these pi's will cancel, leaving us with theta over 2 times r squared. And a lot of times we write this as 1/2 theta times r squared. Okay, so that is the area of the sector of our circle. Okay, and so that's what we're going to be using down here when we actually apply that. This is like our 1/2, and then this is like our r squared, and this is our theta. But what I'd like you to look at is if you were integrating and you had, r in terms, r going from some theta angle alpha to some theta angle beta. So this would be your alpha, and from here to here would be your beta angle. What you're going to do is you're going to be looking at breaking this up into little mini sectors. And I just drew one, but notice that this right here, this little piece is going to be our change. This is going to look like our change in our angle, because like that is going to be equivalent to that. So a very small change in theta. That was a d theta. I know that doesn't look like it. Now that I look at it again, it's like, what in the world did I write there? But that was supposed to be d theta, representing a very small change in theta. And notice that if I had this point on the function, I would be going some angle theta, and then I would be going out some r, right? And then this would be another angle theta. Notice that if this was my theta 1 and this was my theta 2, that my d theta would be my theta 2. Oh my goodness, my pen's not working. My theta 2 minus my theta 1. I just charged it too. But it's like you're doing a sliver of this. And so, but then we're just going to add those up. And we're going to take the number of them to infinity, which we know that, the limit as the number of them go to infinity, and we sum up all of them, just like the definition, k to n. This is going to be equivalent to that integral. So when, think of having infinitely many of these little strips and summing up all these little sector 1/2 r squared, thetas, okay? Summing up all those 1/2 r squared thetas. And when we do that, it's going to end up giving us that integral from alpha to beta. Okay, so just remember that, you're summing up all these little slivers, infinitely many of them. So that's going to give us this area in polar coordinates here. It says if f is continuous and non-negative on the interval from alpha to beta, then the area of the region bounded by the graph of r equals f of theta between the radial line theta equals alpha and theta equals beta is given by the area equals 1/2 is coming from this equation, the integral from alpha to beta, our f of theta is our r squared, so there's our r squared, and then d theta, that is changing, that's our, change. That's our change, small change in theta, and we just basically add those up. And so this is equivalent to, that, like I said, the f of theta is your r. So there it is right there, also written like that. So this is the formula we're going to be using when it asks us to find the area. We just have to figure out, okay, how are we going to know when to start and when to stop, okay? And what I did was I put on your Google Classroom because we're looking at a cardioid for this first example, and I put in Google Classroom this thing called polar functions, and I'm going to show it to you. What did I do with it? Oh, I got to go back this way, sorry. Here it is, polar functions. And they have cardioids on here. Right here is my cardioid. I just took this picture with my iPad camera, and this is a picture in your book. So you can find this in Unit 10, Chapter 10 in your book. Notice that this cardioid is in the form of, and it tells you up here, r equals a plus or minus b times the sine of theta, or r equals a plus or minus b times the cosine of theta. Okay, so it tells you if it's sine theta, it has y-axis symmetry, and if it's cosine theta, it has x-axis symmetry. Ours has x-axis symmetry, so this one has x-axis symmetry. So, because you can see you could fold it along the x-axis here, and it would fold right on top of itself. So that's x-axis symmetry. So this one would be considered the r equals a plus or minus b times the cosine of theta. And when you look at our cardioid, the equation for the one that we're doing in our notes is r equals 1 plus cosine theta. So our a is 1 and our b is 1. So this is a over b equals 1, right? So, and it goes from 0 to 2 pi. That means that to make this entire cardioid, you have to go from 0 to 2 pi. So let's go back to, let's go back to our notes and find the area inside the cardioid. R equals 1 plus the cosine of theta. Now, one thing you could also do is you could find the area of half of it and then multiply it by 2. But what we're going to do, what I decided to do this time, is just do the 1/2 integral from 0 to 2 pi, because I know it's going to take me from 0 to 2 pi to do all of this. And so I'm just going to, find all this area. I'm going to integrate from 0 to 2 pi, and that is fine. And this is our r squared d theta, okay? So the hardest part of this is to know like what your alpha and beta are if they ask you to find a specific piece of it. That is the hardest part. The rest of it is just, really just applying all the things that you've learned. So here we're going to square this. So we've got 1 squared is 1, and then we got a cosine, and another cosine is going to be giving me a 2 cosine theta, and then plus cosine squared theta. And anytime we have cosine squared theta in our integral, or not anytime, but almost anytime, we're going to substitute it with our equivalency for cosine squared from our trig identity sheet. And our trig identity sheet tells us that cosine squared theta is equivalent to our 1 plus cosine of 2a over 2. 1 plus cosine of 2, and I'm going to change the a to theta over 2, okay? And so this is going to be 1 plus 2 cosine theta plus, and I'm going to go ahead and split this up into my 1/2 plus 1/2 cosine 2 theta. And then that is all that I have here. And I went ahead and added another page because this is going to take a lot of work. Not a lot, but more than I can fit on my paper. You might be able to fit it on yours, but if you can't, you might want to just use the back of your page if you have room, or just get a piece of paper and add to it, because a lot of the problems in this 9.6 take a lot of time. Not a lot of time, a lot of area to work, a lot of work area. And by the way, I showed you how I found this out, but I did want to state that that cardioid went from 0 to 2 pi, okay? I forgot to do that. I just looked up and saw it. Okay, so now if I was going to, you could take your 1 and your 1/2 and make it 3/2 if you wanted to. That would just be adding like terms, because you've got 2/2 plus 1/2 is 3/2, and then you've got your 2 cosine theta, and you've got your 1/2 cosine of 2 theta d theta. Okay, so now let's go ahead and start integrating. So we know that this is going to be 3/2 theta. Okay, and if I take the derivative, if the derivative is cosine, that means I must have taken the derivative of sine. And then the 1/2, if the derivative is cosine 2 theta, I need to divide by 2 for the derivative of 2 theta, and then it must have been sine 2 theta. Okay. So now we are ready to use the fundamental theorem of calculus, where we're evaluating this at 2 pi. And I went ahead and took 2 times 2 pi and got 4 pi. So there's my evaluation at 2 pi minus my evaluation at 0. And since the sine of 0 is 0, and 3/2 times 0, this one would go to 0. I mean, I guess I can write it. 3/2 times 0 plus 2 times the sine of 0 plus 1/4. Oh, I wanted to make this fit. 1/4 times the sine of 0. Make that bracket end. But look, all of these go to 0. Okay, so we don't have to worry about that. Some of these even go to 0. So the 2's are going to cancel here. I get 3 pi. The sine of 2 pi goes to 0. The sine of 4 pi goes to 0. And so since this is area, this area is 3 pi over 2 units squared. Okay, so that is the area inside the cardioid. All right, let's go to our example number 2. Now, this was what I wanted to show you. Remember, I don't know if you remember in the last video, I was like, oh, does it go from 0 to pi or from 0 to 2 pi? The reason I said that is because this shape is created, this shape is created in pi radians. Now, if I went from 0 to 2 pi, it just creates it again over itself. So you can't even tell. But if you go back to that page that I was talking about and you look for, I think it's on the second page. Look, it's a rose curve right here. Oh, wow. How did I get that? I don't know what I did there. It's a rose curve. And it has an odd number, example number 2, because actually this function on example number 2 is the exact same function that we used on the last problem that I just made a video on. So you can see that when your n right here is odd, it's going to make that many petals. But if your n was even, it's going to make twice that many petals. Okay? So, and this one has y-axis symmetry. So if you folded it along the y-axis, it's going to fold on top of itself. So, and look, it only goes from 0 to pi to make that thing. So all 3 of those petals are formed just by going from 0 to pi. So when we come here and we start looking at the area, they only want the area of one petal. And I know that the whole thing is going to be made from 0 to pi, okay? So that means that just one of these petals is going to be made from 0 to pi over 3. So if I only want one of the petals, I'm going to go from 0 to pi over 3. 1/2 4 sine of 3 theta squared d theta. And I know from a trig identity that sine squared, I'm going to say u is equivalent to 1 minus cosine of 2u all over 2. That's a trig identity that I'm going to have to use. And when we multiply this out, you'll see what I'm talking about. So I'm going to bring that 1/2 out in front. Integral from 0 to pi over 3. And this is going to be 16 sine squared 3 theta. Okay, so you're just squaring that. And now this is what you're putting in for your trig identity. Your u is 3 theta. So I'm going to pull that 16 out times that 1/2 and get 8. Integral from 0 to pi over 3. And I'm going to say that this is 1 minus cosine of, now we have to think of it as 2 times 3 theta over 2. So 8 times the integral from 0 to pi over 3, and we're going to say 1/2 minus 1/2 cosine of 6 theta d theta. And at this point, since I have an 8, I'm just going to pull that 1/2 out. That's going to make 4 integral from 0 to pi over 3, 1 minus cosine 6 theta d theta. And what we're going to do is we're going to take this now and we're going to bring it up here. This is going to be our example number 2, continued. So we're at 4 integral 0 to pi over 3, 1 minus cosine 6 theta d theta. Okay, that's where we are. And now we're in a good spot to integrate. This is going to be theta minus, and this is going to be 1/6 sine of 6 theta from 0 to pi over 3. And now we've got putting pi over 3 in. And so this is going to give me 6 times pi over 3 is 2 pi. Minus, and then this would be 0 minus 1/6 sine of 0. So 4 times, this one's going to 0. Of course, that whole thing goes to 0. Giving me 4 pi over 3 units squared. Okay? And, you know, basically we just found the area inside here. If they wanted, this is also a way, if they wanted all the area of everything inside, you could have still done this and multiplied by 3 to get all 3 of them. Okay, so just like I said, we could have done on the cardioid, we could have done half of it and multiplied it by 2 because of the symmetry. It's just, you have to be careful because you need to know where it starts and where it stops. Okay, and I think that that probably is the hardest part. Everything else seems to be pretty easy. Got to use some trig identities, but they're not that difficult. Okay, let's look at example 3. Find, the area inside one loop of r squared equals 9 cosine 2 theta. Okay, so I want to show you one of these in our polar functions. I think it's in the first one. There it is. So we have this situation right here on that example, number 3. This is, and the one that we have that we're looking at is r squared equals 9 cosine of 2 theta. Okay, so our a is 3 because look, a squared cosine of 2 theta. Look, our theta goes from 0 to pi. So if I go from 0 to pi, that it's going to sketch this whole curve. Okay, if I went to 2 pi, it would just sketch it again right on top of it. Okay, which that is what we really need to know. But we also need to know where, you know, at what pieces it's sketching it, like at what angles, I guess I should say. So what I did was I took that 9 cosine of 2 theta over here. I just went, oops, sorry. I actually might change the color. Okay. I took 9 cosine of 2 theta and I set it equal to 0. And I divided by 9. That still gave me the cosine of 2 theta is 0. And then I thought, well, what angles, right? What cosine of what is 0? So that I could set my 2 theta equal to that. Well, pi over 2 I have 0. 3 pi over 2 I have 0, dot, dot, dot. So my theta, if I divide by 2, I get pi over 4. If I divide by 2, I get 3 pi over 4. I could also go in the negative direction if I wanted to. I could get negative pi over 4, right? Because if I said it was equal to negative pi over 2, so negative pi over 2 could have been another one that I said, divide by 2 would have given me negative pi over 4. I could have said negative 3 pi over 2, which would have given me negative 3 pi over 4. And so it doesn't tell you that you have to go from 0 to pi, but I'm just saying that by looking at that, we know that that is going to be our where our theta goes from 0 to pi. And so Ugh, this pen. This is our pi over 4. And this is our negative pi over 4. And so I can, if I want just one loop of this, okay? If I wanted one loop, I could integrate from negative pi over 4 to positive pi over 4. And that would be my 1/2. I would take my, now, think about this. You have to solve for r here. So your r is the square root of 9. I think this, oh my goodness. I needed to screw the tip of my pen in. That's why it was doing that. My r is the square root of 9 cosine of 2 theta. So that's my r squared d theta. Okay? So I'm going to go from negative pi over 4 to positive pi over 4 to get my inside one loop of this, okay? So now I've got another page down here. I'm going to go ahead and finish my example number 3 down here. So example number 3 continued. I've got my 1/2. This is my area. This is my area. Equals 1/2 from negative pi over 4 to positive pi over 4. My square root and my square cancel. This is 9 cosine 2 theta d theta. And so, actually, if I bring that 9 out, I could have 9/2. And I know that my integration is going to be 1/2 sine 2 theta from negative pi over 4 to positive pi over 4. So I have 1/2 sine of pi over 2 minus 1/2 sine of negative pi over 2. And the sine of pi over 2 is 1, so that'd be 1/2 times 1 minus 1/2. The sine of negative pi over 2, remember, this is 0, 1, cosine sine. This is pi over 2. But look, this one down here is negative pi over 2, because I would start here and go in the negative direction to get to that one. This is the point 0, negative 1, cosine sine. So this is times negative 1, giving us 9/2 times 1/2 plus 1/2. Well, that's 1. And so I get 9/2 units squared. Okay? Now I'm going to do example number 4, and then I'm going to end it and come back to it on the next video. So this will be example number 4, and then we'll stop until part 2. So find the area of the inner loop of the graph r equals 2 minus 4 cosine theta. Well, remember that we said the inner loop is when your r values are negative and your x or theta values are positive. So if we changed this into y equals 2 minus 4 cosine x, we would be looking for where your y values are negative and your x values are positive. Okay? So if we go and we look at that on our calculator, y equals 2 minus 4 cosine x. let's go do that real quick. I don't even know what calculator I have. Let's see. Why not Desmos? Y equals 2 minus 4 cosine x. And we are looking where our, what did I just say? We are looking for where our y values are negative and our x values are positive. So we're talking about all of these are positive x values, right? Oops. And so I do see from 0 to pi over 3 that I have negative y values but positive x values, okay? I also could go from negative pi over 3 here to positive pi over 3. That would be a good piece of negative, you know, because you have to remember that that even though we say that, for instance, this this inner loop of the cardioid, we might say that it goes from 0 to 2 pi. We could also look at it going from you know, negative pi to positive pi, and that would be a total of 2 pi radians, okay? So we also want to look at like the angles that are being produced. So let me go back to look at this picture. So what I mean by that, we have angles here and angles here where this starts to produce this inner, right? And so we're talking about our pi over 3, negative pi over 3. So from negative pi over 3, I'm going to get my red one, to positive pi over 3, we have created the part that we want to find the area of. So this is what we are going to integrate. We're going to go from negative pi over 3 to positive pi over 3. Now, how else could you have done that? You could have set your 2 minus 4 cosine theta equal to 0. 2 equals 4 cosine theta. 1/2 equals cosine theta. And figured out where your cosine was positive 1/2. Okay, so 1/2 square root of 3. That would be at theta equals a 60-degree angle, pi over 3. We also have it in the fourth quadrant, okay, at negative pi over 3. And so those are, you know, you could have said 5 pi over 3, but you had to think about, you know, how is it happening? And if you went from pi over 3 to 5 pi over 3, it's going to be, you know, going out here. So you have to be careful with that. So negative pi over 3 to positive pi over 3 is going to be a good fit for us. You could have used, what could you have used? You could have used 5 pi over 3 to 7 pi over 3, I think would have done it. But anyway, you know, there's other ways. It's just that this one I think is the easiest. All right, so let's start our area equation. So we've got 1/2 times the integral from negative pi over 3 to positive pi over 3. And then we've got our 2 minus 4 cosine theta squared d theta. And this is going to be our 1/2 integral negative pi over 3 to positive pi over 3. This is going to be 4. I've got a negative 8 and another negative 8 is a negative 16 cosine theta, and then a positive 16 cosine squared theta, d theta. So 1/2 integral from negative pi over 3 to positive pi over 3. I have to use my trig identity for cosine, so this is going to be 4 minus, or for cosine squared, excuse me. You knew what I meant, didn't you? This is going to be your 1/2 plus cosine 2 theta over 2 d theta. And this 16 is going to get distributed. No, I'm squeezing this in. Sorry about that. But I wrote too big on the other one. So this is going to be 1/2 integral negative pi over 3 to positive pi over 3. I'm going to add my 4 and my 8, giving me 12 minus 16 cosine theta plus 8 cosine 2 theta d theta. Now I can see that I can factor a 4 out. If I factored a 4 out, it would give me 2 here. And this would be 3 minus 4 cosine theta plus 2 cosine 2 theta d theta. Now I can go ahead and integrate. I've got 3 theta minus 4 sine theta. And then I'm going to take that 2 and divide it by 2, right? So that's going to give me sine 2 theta from negative pi over 3 to positive pi over 3. So 3 times pi over 3, my 3's are going to cancel, minus 4 times the sine of pi over 3 plus the sine of 2 pi over 3 minus negative 3 pi over 3 minus 4 times the sine of negative pi over 3 plus the sine of negative 2 pi over 3. Yay, now I can finally come in down here. So this is going to be pi. Now, let's think about pi over 3 here. We've got a 60-degree angle. So our 4 minus 4 times the sine is going to be 4 times square root of 3 over 2. Plus, and then we've got the sine of 2 pi over 3, which is over here. And again, 60 degrees, square root of 3 over 2, minus, this is going to be negative pi. Now we've got negative pi over 3. So this is going to be negative square root of 3, 1 and 2. So the sine of that one of negative pi over 3, so it's going to be minus 4 times negative square root of 3 over 2. Plus, and then we've got all the way over to negative 2 pi over 3. In the third quadrant, the sign is, again, negative square root of 3 over 2. Divide by 2, divide by 2. Pi minus 2 root 3 plus square root of 3 over 2. This is plus pi. This is negative times a negative 4 is a positive 4, but then I have to multiply it by a negative, and that's going to be negative, and then the 2 cancels with 2 and the 4. Negative 2 root 3. And then this negative times that negative, positive root 3 over 2. So I've got 2 pi. I've got negative 4 root 3, and I have positive square root of 3. 4 pi, and these two together is going to be negative 3 root 3 times 2. It's going to be negative 6 root 3. Now, how would you check yourself? Go to your calculator and put this original, the original equation in, and you should get 2.174 units squared. Okay, and that is equivalent to that. So the 2.174 should be equivalent to 4 pi minus 6 root 3 units squared. And I'm going to go ahead and end it here and pick up the rest of this with our next part 2